no pointers expressed in the language. We, of course, use them in our LLVM IR to do things like in and out pointers and such, but we don't have pointers as such. We have limited use of arrays in the language. Currently, at present, we only allow input float arrays, which is something we hope to make better. And we have no user-defined structures. Okay, so the process of making an LLVM kernel run on the CPU, or a kernel run on the CPU via LLVM is, first we have to take our evaluate pixel function and all the attendant subordinate functions and turn them into LLVM IR. Additionally, we have to produce a main loop. On the GPU is kind of like the pixel program running over the individual pixels is part of the execution sort of model of the GPU driver. And this, sets up vertices and sort of tessellates them and does the whole 9 yards. And it's kind of there for you. You don't worry about it. But on the CPU, we have to set up our main loop. And this does things like translate our requests, which are on this theoretical image plane, and translates them down into like pixel coordinates on the grid, so we know exactly what we're talking about. And then on a per pixel basis, it calls the evaluate pixel function, and it calls the set pixel function, which squirts it into the destination buffer. Additionally, so we have this main loop. We have this main loop external. One of the issues that came up for us was when we were pinging the jitter on calls from many cores all at once. This was causing us a little grief, and it was also hitting a lot of these stub functions or curry function compiles, and we decided to get rid of that. And so we create this main loop external, which basically takes all the parameters to this, takes pointers to all the parameters to this, lays them down as a structure of pointers here, so that inside main loop external, it just load, call main. In the outside world, it looks like a void star array, and sort of lays down in memory nicely, and allows us to ping it from a whole bunch of cores all at once and not have any troubles. Just one thing to mention about that. This is a shipping piece of software, and so we stabilized around LLVM 2.2. So if I make any kind of, hey, this thing didn't work as well as I hoped it would, that's because we're about 6 months behind right now in terms of the LLVM mainline. So keep that in mind. Oh, and a lot of callback functions for various intendants and such. So here's our identity filter. Here's our LLVM IR identity filter, and with a number of things called out in red, which I would like to make better in the future. So the image star up there, that's basically a big LLVM structure with things like width, height, the buffer, the format, the pixel aspect ratio, the reciprocal, basically also pixel aspect ratio, things like that. And it would be really long, so I just made it image. So evaluate pixel takes in this sort of a float star, this a pointer to a vector it's trying to produce, and it takes in a vector out coordinate. Has to extract these things because the sample pixel callback is, that takes in 2 floats, not a float 2, and so we have a lot of this kind of setup for the purposes of calling sample linear. There's a couple things that caused me some grief. In particular, some of the stack alignment issues on Windows. As of LLVM 2.2, forced me to use a lot of unaligned loads and stores and such. But I think that's all been fixed now, so I'm going to be making that better soon. And I'll talk a little bit more about kind of things that we didn't do kind of quite right in our construction of our LLVM IR, and that we're going to make better in the next go around. So the main function kind of looks like that. Our external main, like I said, takes in this sort of this structure of pointers to parameters, and main external, and this is just in C, just loads and calls. And that turned out to be a pretty useful thing to do. All right, so can't give a talk on filters without showing some. So here are some filters that we generated via PixelBender. Kind of a goofy sort of make little circles. That's actually really easy to write. in a language where you get called in every pixel. Allows you to do the circles kind of implicitly, which is cool. The twirl, which I'll show you in a minute live. Black and white, sort of a fracture tint there thing. This is a colorization. We do a lot of color space conversions at Adobe, and being able to do them on a GPU is pretty cool. And then we have this sort of polka dot twirl combination, sort of that one plus that one equals that one. And pretty cool. So we made a toolkit release available quite a while ago, and we immediately got a lot of interest. And admittedly, some of our interest comes from, in addition to us running on the toolkit and running in some unspecified applications that I can't talk about, we have announced that we additionally have a path that we can compile down to this thing called Hydra bytecode. Our language used to be called Pixel Hydra. Now it's called PixelBender. So I mentioned someday that will become PixelBender bytecode. That Hydra bytecode can be loaded into the Flash player. And so the Flash community is huge, and so they got really excited about PixelBender, and so they've been producing a lot of various kernels. People started doing things that we really didn't expect, like writing fractal generators in 3D, sort of creating all the 3D math themselves within using our primitives. And like I said, some guy wrote a ray tracer. And I told some people at lunch, some guy wrote a ray tracer in PixelBender. We saw that last week. Here's a couple of mine. The top one, I just have to show mine. Like I said, I come from a graphics background, so the top one is basically image warping using radial basis functions. I'm using a 2D B-spline because I like 2D B-splines, and they have compact support, and so they have local refinement and blah, 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 blah. So I was able to take this picture of, at SIGGRAPH last year, of a little otter at the San Diego Zoo and turn him into a snaky one over there. This picture I took in Fiji with my underwater camera, and basically what I did with this filter is I sort of input was a bunch of pixel centers for cells in a Voronoi diagram, and it sort of implicitly calculates the Voronoi diagram and then tints the resulting image by the value of the pixel at the center of the Voronoi cell. So, and this was for our PixelBender contest at work, and I'd like to announce that this was the winning entry to our show, which was a little disappointing because I really liked. I thought the math on the radial basis function image warping was kind of more fun to write. Okay. Actually, let me. What's the? Oh. Okay. Well. All right. I'll do a quick one. All right. So. All right. So. All right. So here's the this is the is negative one that we wrote earlier.